communication network in the mid-1990s. If we look at the same data, this is on this logarithmic scale, on a linear scale, it looks like this. This is the same data on a linear graph. And we live in a linear world. This is how we experience technology. To the casual observer, it looked like the World Wide Web came out of nowhere in the mid-1990s. But if you looked at this progression, this exponential progression, which you can see on a log graph, you can see it coming. We're shrinking technology, factor of 100 per 3D volume per decade, not just electronic, but also mechanical. And we're building the systems now that were contemplated in Eric Drexler's 1986 book, 20 years ago, which ushered in the field of nanotechnology. And I talk about dozens of examples of little machines being built molecule by molecule that is now feasible. And a big example of that, or the most, I'd say, notable example, is actually building systems that can go inside the human body and brain and perform therapeutic functions. And that might sound very futuristic, but we're already doing it today. There's 4 major conferences on biomems, biological microelectronic mechanical systems, of building blood cell-sized devices that can perform therapeutic functions inside the body and brain. The experiments today are largely animal experiments, but they're really quite impressive, and some of these are gearing up for human trials. So one scientist actually cured type 1 diabetes in rats with a nano-engineered device, 7 nanometer pores, lets insulin out in a carefully controlled fashion, blocks antibodies, because type 1 diabetes is an autoimmune disorder. And this actually cures type 1 diabetes in animals. And they're now gearing up for human trials. Scientists at MIT built a nano-engineered blood cell-sized device that performs 5 consecutive functions. It detects the antigens specific to cancer cells. When it detects them, it latches onto the cell membrane, burrows inside the cell, detects that it's inside the cell, and then releases toxins and destroys the cell, and also self-destroys. So this is a pretty complex procedure. This actually works. It's undergoing animal trials right now. So this is today. We also have devices bigger than blood cells, but pretty small, that you can actually program from outside the body. For example, if you have Parkinson's disease, you can have the corpus of cells that are destroyed by Parkinson's disease replaced with a computer that's placed inside your brain. It's pea-sized. And the neurons in the vicinity, which used to get signals from the biological neurons before they were destroyed by the disease, now get signals from the computer, and they're perfectly happy. And this hybrid of biological and non-biological intelligence works just fine. And the latest generation of this FDA-approved neural implant allows you to download new software to the computer inside your brain from outside the patient. And this is today. So if you apply what we can do already and apply this billion-fold increase in the power of these technologies over the next 25 years, and a shrinking in key features and three-dimensional volume by a factor of 100,000 in that same time period, you get some idea of what will be feasible with these programmable blood cell-sized devices, which will be able to go inside our bodies and brains and keep us healthy from inside. You're looking here at a design of a robotic red blood cell. Now, red blood cells is something we have reverse engineered. We understand how they work. And it brings up an interesting observation about biology, which is, on the one hand, it's very intricate and complex. On the other hand, it's very suboptimal. Biology made certain assumptions early in evolution that it can't revisit, like building everything out of proteins, until it gets to the point where it designed a species that's intelligent enough to go back and re-engineer biology. And this is a good example of that. These robotic red blood cells are about 1,000 times more powerful than your biological red blood cells. And a conservative analysis indicated if you replace 10% of your red blood cells with these respirocytes, or robotic red blood cells, you could do an Olympic sprint for 15 minutes without taking a breath, or sit at the bottom of your pool for 4 hours. So, honey, I'm in the pool will take on a whole new meaning. And it'll be interesting to see what we do in our Olympic contests. You might say, well, we'll ban them. Then we'll have the specter of high school kids in their gymnasiums routinely outperforming the Olympic athletes. But it's not clear we should ban them. In fact, I don't think we should. We should ban steroids, because the reason is steroids are bad for your health. If you don't ban them, then you're forcing athletes to do something that's bad for their health in order to be competitive. And they feel that pressure anyway. But these actually will be good for your health. They'll lead to better oxygenation of your tissues. You'll be able to survive, let's say, stop the stopping of your heart for hours rather than minutes and so on, we will ultimately go beyond normal human capabilities, physically and mentally. And to come back to our exponential growth of computing, is the computers of the 20th century projected into the 21st century. We'll have supercomputers that are as powerful as human brain, at least as far as hardware computation is concerned, by 2010. $1,000 of computation will match human brain by 2020. And this is really a mainstream view. When people have studied this, we'll have plenty of computation, speed and memory in computers to simulate the human brain. But then the question is, will we have the software? Or will these just be very fast calculators? And the secrets of human intelligence, the methods, the content, the algorithms are not hidden from us. The primary source for understanding how human intelligence works will be understanding the human brain itself, and it's not hidden from us. But actually, a few years ago, it was hidden from us. You've probably seen, they appear in magazines, fMRI images inside the human brain. They're quite interesting, but they're not good enough to actually understand how the brain works. Someone's solving a logic problem, you see this spot in their brain light up, and so we get the idea that
so happy we alive, we together can survive.
We are just a shell of another self, of another self. Whose priority is to live and learn, yet to let it be. But those we get trapped in, we're kinda stiff, get kinda thin, so we gaze through the atmosphere, and in our hearts we hear.